Okay, this is not really meant to be a serious tutorial on K divergence, so I'm not going to go into topics such as information theory and entropy. What I will try to do instead is to hopefully demonstrate to you why K divergence makes sense as a measure of quote-unquote distance between distributions. So here I have plotted the probability density functions, or PDFs, of two Gaussian distributions. I'm going to refer to the blue curve as the P distribution and the yellow curve as the Q distribution. And our goal for today is to essentially try to figure out a way to compute the quote-unquote distance between these two distributions. And in this way, we are going to gradually build up to K divergence and hopefully help you make sense of the K divergence equation. So since we have the PDFs and therefore have a way of computing the probability for sampling any arbitrary x from either distribution, I think you're going to agree that a reasonable first idea for comparing these two distributions is to just simply compare their probabilities for sampling the same x. Ideally, we would like to do this across all values of x, but we cannot really feasibly do that. So what we do instead is that we select a few points of comparison, a few values of x, and then we compute the probabilities for sampling those x values from either distribution. So we get these px and qx values, and then we compare each pair of px and qx. The comparison is done by taking the so-called log ratio between px and qx. And the ratio bit should be fairly easy to understand because, well, if px is larger than qx, then we get a ratio that is larger than 1, and vice versa. But on top of the ratio, we also apply a log base 2 operation, and that might be confusing to some people. Well, the reason for applying this log base 2 operation is actually rooted within information theory, so unfortunately we cannot go into more details. But for our purpose as users of the K divergence, it suffices to know that the log base 2 operation does not actually change that much about the comparative property of the ratio. So for example, if px is larger than qx, and therefore if we get a ratio that is larger than 1, then log base 2 of a value that is larger than 1 is going to be a positive value, right? And likewise, if px is smaller than qx, then we get a ratio that is smaller than 1, and log base 2 of a value that is smaller than 1 is going to be negative. So the outcome of this log ratio calculation is going to be indicative of the comparison between px and qx. And now that we have compared between px and qx at every point of comparison, the next obvious question becomes, how do we combine them? How do we combine these individual log ratio computations into a final score, a final distance, quote-unquote distance, between these two distributions? Well, maybe your first idea is to just simply average them. But unfortunately, that is not going to work because as you can see here, there are some log ratios that are positive and there are some other log ratios that are negative. So they're going to cancel each other out. And moreover, because PDFs integrate to 1, the average, the fair unbiased average among these log ratios is actually going to always approximate 0, regardless of how different the two distributions are. And in order to understand this intuitively, you can remember that PDFs integrate to 1, and therefore the area under the curve of the PDF can be considered as a sort of limited resource. So it's almost as if you were to boost up, for example, the P curve at some point, that boost needs to be compensated by other points of the P curve being like lower. So it's almost as if every positive log ratio, every part where px is larger than qx, needs to be compensated by another negative log ratio, another point where px is lower than qx. So they're always going to, their fair average, their unbiased average, is always going to approximate 0. And obviously, if the average among these, if the fair average among these log ratios is always going to approximate 0, then we don't have an informative measure of distance, right? Because it's always 0 regardless of the difference. So how do we address this problem? Well, as it turns out, we can make this work by just making a single, very simple modification, and that is to use a weighted average instead of a fair average. And the general idea is that instead of averaging all the log ratios fairly, we give more weights to the positive log ratios and less weights to the negative log ratios. And therefore, they're still going to cancel each other out, but they are no longer going to always cancel each other out towards 0. And with that, we get ourselves an actually informative measure of quote-unquote distance. And a natural choice for such a weight is just the px value, right? Because, well, as we just said, if px is larger than qx, and therefore if the log ratio is positive, then px is likely going to be large. And likewise, if px is smaller than qx, and therefore if the log ratio is negative, then px is likely going to be small. So by weighting our average with px, we automatically give the positive log ratios more weights and the negative log ratios less weights. And with that, we get ourselves the same Cal divergence equation as the one on Wikipedia. This here is the log ratio, this here is the weight, and this entire expression just essentially amounts to doing a weighted average among the weighted log ratios of all points of comparison. And here I show an example of how this is done when we have 4 points of comparison. So here we have the px and qx values, and we take the log ratio, and eventually we take the weighted average. But maybe you have noticed this double vertical line symbol here, and you're wondering what this means. Well, in short, this double vertical line here, means that this calculation, this Cal divergence calculation, is a measure that goes from P to Q. And to be more explicit, that means that Cal divergence is not symmetric. And therefore, Cal divergence from P to Q is not the same as the Cal divergence from Q to P. And by the way, you might have also noticed that I kept using the word distance in quotes. Well, that is because in order for a measure to be considered as a distance, it needs to be symmetric. And because Cal divergence is not symmetric, it cannot be seriously considered as a distance. But in practice, we often just use it as a distance. And this here just shows a simple mathematical proof of why that is the case, why KL from P to Q is not the same as KL from Q to P. And we do that by taking the difference between the two and showing that the difference is not 0. But if you are after the intuitions, then maybe you can return to the Cal divergence equation and pause for a moment and think why this weight here is px and not qx. Could this still work if we use qx here as the weight instead of px? Well, it's still going to work, right? Except now the entire thing is going to be flipped upside down. So whereas before when we used px as the weight, larger Cal divergence would have meant larger distance between the two distributions. Now with qx as the weight, actually smaller Cal divergence is going to mean larger difference between the two distributions. So if either using px or qx as the weight would have worked in this context, and we have chosen using px as a convention in Cal divergence, that by itself can be considered as a sort of bias towards the first of these two distributions that we're comparing. So hopefully that helped with your intuitions. And there is just one final thing I want to mention before we conclude. And that is that Cal divergence compares between two distributions in the distribution space and not the parameter space. That might sound like a fancy sentence, but all this is saying is that Cal divergence directly compares the probabilities instead of the distribution parameters. So for example, here, when we are comparing between these two Gaussian distributions, we're comparing directly the px and qx values instead of the mean and covariance values. And this is a good thing because comparing in the distribution space means that Cal divergence is neutral to the parameterization of the distribution. So the two distributions that we're comparing can have parameters that operate on entirely different numerical scales. They can even be two different kinds of distributions altogether. And all the methods that we have just discussed are still going to apply. So Cal divergence is a very easy to use and a very generalizable measure. And I think that makes Cal divergence very useful. And finally, I just wish to show to you a simple demo for the Cal divergence that I've written. So as you can see here, if we make the parameters for the two distributions similar to one another, so like this, then the KL divergence up here is going to approximate 0. And if I were to kind of swap the parameters between these two distributions, so now the P distribution is what Q used to be, and vice versa, then the KL divergence now is actually different from the KL divergence that we had before. So hopefully that's just helped reinforce your intuition why the KL divergence is not a symmetric measure. I'm going to post the link to the codes in the description, and you can play around. So in this case, we are using 4 points of comparison, but you can tweak this parameter here to make it use more points of comparison. So yeah, there are now 5 lines, but as you can see, the texts are a bit clustered up. So you might want to be cautious with using too many points of comparison. So that's it.